Dear students, in this video we will discuss our topic stability of structures of Unit 1 structural analysis. So here structural stability is the major concern of the structural designer, and to ensure the stability a structure must have enough support reactions along with the proper arrangement of members. The overall stability of structure can be divided into external stability and internal stability. So let's discuss our external stability. So here in external stability for 2D structures, we have for stability of 2D structures, there should be no rigid body movement of structures due to loading. So it should have support in x direction, support in y direction, and no rotation in xy plane. So there should be three conditions of static equilibrium which should be satisfied. That is your summation of fx is equal to 0, summation of fy is equal to 0, and summation of mz is equal to 0. Summation of fx is equal to 0 means to prevent your deflection in x direction. And summation of fy is equal to 0 means to prevent your deflection in y direction. Similarly, summation of mz is equal to 0 means to prevent your rotation in z direction. Okay. So for stability in 2D structures, following conditions also be satisfied. So what are these conditions? That first is your there should be minimum 3 number of externally independent support reaction. Okay, so minimum 3 number of externally independent support reaction have to be so this should condition should be satisfied for your stability in 2D structures. And second condition is all reactions should not be parallel, otherwise linear instability will set up. Okay, so you can refer this diagram. This is your unstable structure here, as your this is your roller support RA, and this is your roller support again C, and support B. So we know in roller support only one vertical reaction which is normal to the support acts, that is RA here, RC here, RB here, and all these three reactions are parallel. So linear instability will set up here. So that's why this structure is unstable. Okay, so let's move on to the next condition. This is your all reactions should be not be linearly concurrent, otherwise rotational instability will set up. Here you can see this is unstable structure again, because this is your Ra reaction, Rc reaction, and Rb reaction meeting at one particular point, and here rotational instability will set up. That's why this structure is unstable. Okay, linear concurrent. Okay, so these are some conditions, and again we should have a reaction should be non-trivial. Reaction should be non-trivial means there should be enough magnitude and enough difference between them. Okay, so reaction should be non-trivial, enough magnitude have to be there. So for stability in 3D structures, we have this is our stability in 3D structures, that in 3D structures there should be a minimum 6 number of independent external reactions to prevent rigid body displacement of structure. Okay, so the displacement to be provided are delta x, delta y, delta z, theta x, theta y, and theta z. For 3D structures, we should have six independent equations. That is delta x, delta y, delta z, theta x, theta y, and theta z. Okay. So therefore, there will be six equations of So these there will be six equations of static equilibrium rise. Summation of fx is equal to 0, summation of fy is equal to 0, summation of fz is equal to 0, and summation of mx, my, and mz is equal to 0 for stability of 3D structures. Okay. So for stability in 3D structures, all the reactions should be non-coplanar, non-concurrent, and non-parallel. Okay. So these are the some conditions for 2D and 3D structures, and I would like to share you that if a structure is constructed from elastic members, then small elastic displacement may be permitted, but small rigid body displacement will not be permitted. Okay, so for structures constructed from elastic members, it should have a small elastic displacement, but no small rigid body displacement will be allowed. Okay, in the structural analysis. So here, now let's go and with certain examples on stability. Okay, so here check stability of the following structures, as this is your structure, as we have a hinge support, this is your hinge support, and this is your roller support here. So this is your AB member, this is your BC member. Okay, so we have to check whether it is stable or unstable structure. Okay, so I draw this equivalent diagram or idealized diagram, as if I remove the support, that at we know at this particular hinge point in support we have our two reactions. Okay, one is horizontal reaction, that is HA, and one is vertical reactions over hinge support. Okay, so this is RA, and here we know at the roller support we have one reaction which is normal to the support. So this is your HC, which is normal to the support. So this structure is stable, as we know that is since these reactions are non-parallel and non-concurrent, so that's why this structure is stable. Okay, so non-parallel and non-concurrent we have to remember. Okay, so let's take some other example. Like this is the structure, like A is your roller support, this is AB member, this is BC member, then this is your hinge support here. Okay, so at hinge support we have two reactions, one is vertical and another is horizontal here. So this is our HC and this is our RC vertical reaction, and at roller support we have a reaction normal to this support. So this is your RA point, and I show here a close zoom effect, that is your, if I'm considering here this point C point, so you can see here this is your reaction RA which is acting here. Okay, at this point, and this is your horizontal reaction at C, this is HC, and this is your RC. So overall this structure is unstable, as since all the reactions at C are concurrent. Okay, so these all reactions are concurrent at C, so that's why it is unstable structure, as we discussed in our conditions of 2D stability of structures. So that's why this is an unstable structure at, as all our reactions are concurrent at C. Okay, let's take one another example. Like this is your beam, continuous beam it is. This is your roller support A, again roller support B and C. Okay, if I draw the idealized diagram, that is at roller support we know one vertical reaction normal to the support, again one vertical reaction RB and one vertical reaction RC. This is again your unstable structure, as we all know that all these three reactions are parallel. Okay, so all these three reactions are parallel, that's why it is your unstable structure. Linear instability will set up in this structure, so that's why it is unstable. Okay, so let's move on to next example, that this is your support, roller support here, and this is your member AB here, this is your hinge point, and this is again your hinge point, and this AB member and BC member, BC and AB and CD members are connected by your internal link. Okay, so this is your internal link member and this is your internal hinge here. B is your internal hinge, C is your internal hinge. Okay, and this is your CD member supporting at hinge support here. So we have here, if I draw equilibrium, if I draw here our free body diagram. So let's take this AB part here. So I draw this AB part here, and this support, roller support, we have one vertical reaction, that is RA here. Okay, so at B point we have one horizontal reaction here, this is a hinge, this is a horizontal reaction here. Okay, and we have a RB value here. Okay, so to nullify this RB effect, we have in this part, this is our vertical part here, and vertical part RB value in upward direction again. So RB value in downward direction, RB value in upward direction gets nullified here, and this is our HA is in this direction and HB in this direction. Okay, so this is your overall free body diagram here of AB part, and here for BC part, at C point we have our internal hinge here. So here this is horizontal reaction at C in this part, and vertical reaction RC in downward direction. Okay, so for member CD. If I draw the free body diagram of member CD, so here RC downward here, so to nullify it, RC upward here. Okay, so HC in right direction, so HC in left direction. So this is a free body diagram here. And at D support, we know here we have our hinge. So this is our hinge support, and we know at hinge support we have our two reactions, that is in horizontal direction HD and in vertical direction RD. Okay, so this is a free body diagram, and since the member AB, since this is a member AB which can move horizontally, okay, so this member AB can move horizontally here, so without any restraint. Okay, so that's why this overall structure is unstable structure, because here the member AB can move horizontally without any restraint. Okay, so that's why here summation of fx is not equal to 0. So condition is violated here, so that's why this structure is unstable. Okay, summation of fx should be equal to 0, okay, for stability of structure, but here summation of fx is not equal to 0, so as member AB is not restrained in this direction, so that's why this is your unstable structure here. So these are some examples. Based on this, we can check whether our structure is stable or whether our structure is unstable. Okay, so let's move on to another part of stability, that is your internal stability. Okay, so for the internal stability, no part of the structure can move rigidly relative to the other part, so that the geometry of the structure is preserved. Okay. So, however, small deflection, elastic deformations are permitted. So that the geometry of the structure is preserved, small elastic deformations are permitted. Okay. So to preserve the geometry, enough number of members and their adequacy arrangement is required. Okay. So for the geometric stability, there should be not be any condition of mechanism. Okay, so mechanism is formed when there is three linear collinear hinges. Okay, so if I'm considering three collinear hinges, to preserve the geometric stability there should not be three collinear hinges. Okay, so we should not have three collinear hinges, and mechanism should not be formed. Okay. So for 2D truss, the minimum number of members needed for geometric stability are m is equal to 2j minus 3. Okay. And for 3D truss, the minimum number of members needed for geometric stability is 3j minus 6, where j is the number of joints in the truss, and m is equal to member required for geometric stability. Okay. So all the members should be arranged in such a way in the truss that it can be divided into triangular blocks. Okay, you saw your truss that it should have your triangular blocks. Okay, so here for the overall stability of truss, the minimum number of members should be present. M is equal to 2j minus 3 for 2D truss, and M is equal to 3j minus 6 for 3D truss. Okay, so there should be no condition of mechanism also exist. Okay, so these are some points for internal stability, and let's quickly solve some examples on geometric stability. So I summarize here that for internal stability, for minimum number of members should be 2j minus 3, and for 3D truss it is 3j minus 6 here. J is equal to number of joints in the truss, M is equal to member required for geometric stability, and here you can refer these empirical equations. Okay, for now let's move on example on geometric stability of truss. Okay, so here you can see that this is your truss, and this is your left portion here, and this is your right portion here, and this is your support, hinge support here, again this is a hinge support here. For right panel you can see this right panel, here we have joints is equal to 4, that is 1 2 3 and 4 joints here, but um, members presently number of members present here are 4 also, one member, two member here, three member or four member. So 1, 2, 3, 4. These are present members in the right panel here. Okay, but minimum number of members needed for geometric stability is 2j minus 3, we know. Okay, so for minimum number of members needed is 2j minus 3. So if I put my value of j here is 4 minus 3 is 8 minus 3. 4 to the 8 minus 3 is 5. Okay, so here your right panel is deficient. Okay, so here your right panel is deficient. We have to ensure one additional member. Okay, so for geometric stability, but we have our present members are 4 here, because present members are 1, 2, 3 and 4. Minimum member we required are 5. Okay, so we are left with only one member here. Present members are 4 and members needed are 5. Okay, so here you can say this right panel is deficient. Okay, deficient with one members. Okay, so for left panel you refer here, this is your left panel. Okay, here number of joints are 1, 2, 3, 4, 4 again joints. So number of joints is equal to 4, and number of members present members, number of members present are 1, 2, 3, 4. This is your 5, this is your 6. So 6 members are present for left panel, and but minimum number of members needed will be given as we know 2j minus 3. Okay, so number of joints j is equal to 4 here minus 3. So 4 to the 8 minus 3 is 5. Here you can see for this left portion we have minimum members required are 5, and hence the left panel is over stiff because we have our members 6 here. We have our 6 members here and minimum number we required are 5. So here we are having your left panel as over stiff. Okay, because number of members presents are 6 and minimum members we required are 5, so left panel is over stiff. Okay, so therefore arrangement of members is not adequate, hence right panel is unstable. We can say right panel is unstable and left panel is over stiff. Okay, so this is our statement and this is our conclusion for this example. So right panel is your unstable and left panel is overstiff. Okay, so you can solve by your own also. And this is another example, like we have a truss here. This is a hinge support, this is a hinge support, and minimum numbers of members needed is equal to 2j minus 3, we know. Number of joints here is 1, 2, 3, 4, 5, 6. 6 joints minus 3 is 9. So minimum number of members needed is 9, and we have our present members are 7 here. 1, 2, 3, 4, 5, 6, 7. Present members are 7 and number of member needed are 9. So hence above truss is geometrically unstable. Okay, and it can be called as deficient structure. Okay, so number of deficiency is equal to 2 because we have to ensure our minimum number of members as 9 and we have in our truss number of members are 7. So we are deficient with 9 minus 7 is 2. So number of deficiency is equal to 2. So that's why this truss is geometrically unstable and is called as deficient structure. Okay, so now let's discuss the overall stability. So what is this overall stability? So for overall stability, external stability is compulsory. Okay, so for the overall stability of any structure, external stability is compulsory. If our external stability is satisfied, then our overall structure is stable. Okay, so in some cases structure is overall stable, but it may be over stiff externally or deficient internally. Okay, overall the structure will be stable, but condition would be this is over stiff externally or deficient internally. It means your support reactions are more than 3. Okay, so it means your support reactions are more than 3 and number of members are less than 2j minus 3. Okay, so for deficient internally, the number of members are less than 2j minus 3, and for over stiff, we should have a support reactions more than 3. So this condition you have to keep in mind. So for overall stability, your external stability is compulsory. Okay, so here you can refer one example. Yes, this is your truss, and here this is having a hinge support here, and this is having a hinge support here. Okay, so hinge support, we know there are two reactions, one horizontal reaction and vertical reactions act, and here again two reactions act. And you can refer that external reactions at the supports are external reactions 2 here and 2 here. So number of external reactions are 4 here, and number of members presents here is equal to 10. Okay, you can count it: 1 2 3 4 5 6 7 8 9 10. So number of present members are 10 here, but minimum number of members needed are 2j minus 3. We know minimum number of members needed will be 2j minus 3. So number of joints are 7 here. You can count it again: 1 2 3 4 5 6 7. Okay, so 7 are the number of joints here. So 14 minus 3 is 11. So number of members needed are 11, and we have our number of present members are 10. Okay, so it means a truss is deficient to 1 degree. Okay, so we have to be ensure that minimum number of members have to be 11, but in present we have a 10 numbers. So we are having a deficient to 1 degree. 11 minus 10 is 1 degree. So but the truss is overall stable. Okay, because there is one extra redundant reaction which give prevent geometric deficiency. Okay, so overall the truss is stable. So thank you so much for watching this